Okay. Hello, everyone. I'm Kazuyoshi Kanamori from Kyoto University, and I'm a chemist and working on aerogels and other porous materials and gels. So I heard that many people are coming from different fields. So I tried to give you good insights into our research as easy as possible. So today, I will talk about our recent aerogel research with the title, Making Aerogels Different. The aerogels are usually very friable, brittle, mechanically weak material, but we somehow want to improve the mechanical strength and mechanical flexibility for better applications. So we are trying to make aerogels different by engineering chemical composition and microstructure for superior mechanical performance. So I will start. Before the talk, this is me. I'm actually from Hiroshima, Hiroshima City. Graduated from Shudo High School, Hiroshima. So I'm a fisherman, like these pictures. So and I graduated from Kyoto University 2005, many years ago already. So now I speak a little bit Kansai dialect in Japanese, Kansai Ben, but I have in my mind, Hiroshima dialect. Still have Hiroshima Ben. Okay, so after finishing my PhD, I got a assistant professor at Department of Chemistry, Kyoto University. Until now, I'm working. So my favorites are fishing and Hiroshima Toyo Cup. Do you like baseball too? The red color uniform costume team. Okay. So, and my expertise is like inorganic and polymer chemistry. I like materials. So in the chemistry fields, people are a little bit divided into different fields, like inorganic chemistry, organic chemistry, polymer chemistry, but I'm playing in all the fields in chemistry. Okay, so this is the slide that I already gave you. So I hope you found it. And this talk will be on chemistry, materials, colloids, gels, and mechanical properties and porosity in the material. And so the major open question in aerogel field is like how to improve mechanical durability of aerogels for better research, for better applications. And I'm motivated by rational controls over network structures. I know you're working on the chiral knotted materials. And I think the cross-linking of the network is also like knotting points that can act as unique cross links for different functionalities and mechanical uniqueness. So I will show some about this. This is one page slide for my talk. Using soldier chemistry, I would use the laser pointer. That's okay here. Should be better here. Good. So we use soldier chemistry from alkoxysilane molecule like this, and we can prepare the transparent aerogels, which is compressible and also bendable sometimes. And the microstructure varies from the network of spherical colloids. And also we are recently working on the aerogels with fibrous skeletons networks. Okay, so I think many of you already know about aerogels, but so I go quickly here. And aerogels are like transparent, mesoporous materials. On my hand, this is the aerogel. So this is highly porous and transparent material. So the refractive index of the aerogel is quite low. So it's difficult to see the interface between the solid and air. So it looks more like air rather than solid. So sometimes it is called like frozen smoke. So this is because of the high porosity, sometimes typically over 90%, sometimes 95%, 99%. And because of the mesoporous structure, the scattering of visible light is suppressed. So the aerogels are like a transparent material. And also because of the high porosity and very small pores, the thermal conductivity of aerogels are very low. So many researchers are working on aerogels for applications to thermal insulation materials. So we are also trying. And for other aerogels, other various types of aerogels are developed. This is the polyimide aerogel. It looks yellow because of the molecular structure, and typically they are not transparent, but they are mechanically very durable. Like here, you can find the polyimide aerogel. And also, this is the polyurethane aerogel. It is not yellow, and but it is not transparent typically, and they show high mechanical strength as well. And this one, you can see the Professor Smalyukov's very attractive materials, cellulose-based aerogels. And yeah, this is a very good one because they can produce the aerogels by the row-to-row process, which is very important for industry applications. So coming closer to industry, I believe. And also there are some composite like aerogel, silica aerogel, fiber composite like this, and aerogel render to broaden the application and ensure the better handling abilities. Okay. So this is why people are interested in aerogels. This is one reason. They have very low thermal conductivity. These blue lines are the thermal conductivity values of the common thermal insulators like glass wools and the polymer forms. And you can see here, silica aerogel typically has a thermal conductivity lower than those common thermal insulation materials. The value is like somewhere between 10 to 20 milliwatts per meter per Kelvin. Okay, and so we can say that aerogels are the best thermal insulation material, but we have to improve the mechanical property to make it available in the commercial market. So this slide shows you that how the silica aerogels are prepared. This is typically prepared by the sol-gel. So it is called sol-gel process. Typically starting from alkoxysilane, like this molecule. This is called tetraethoxysilane. So this is called TEOS. And this is the overall reaction. TEOS reacts with water to produce silica gel network and alcohol. And this overall reaction can be divided into two different types of reaction. One is hydrolysis, which converts the alkoxy group to hydroxy group, like this, with a reaction of water in the presence of acid or base catalyst. After that, this SiOH, it is called silanol group. Silanol groups are condensed like this reaction to form the silicon oxygen silicon bonds. So repeating this condensation process, then you can have the three-dimensional network, colloids, and then form the gel. And the condensation reactions can be also divided into two parts. One is the reaction between the two silanols. The other is reaction between silanol and one alkoxy group. This is slower. So in this way, we can prepare the gels from, this is schematic illustrations from the solution containing still no colloids in the solution. And the reaction goes, hydrolysis and the polycondensation. Then you will have a solve, which means the dispersion of colloids in a liquid. And then after the reaction proceeds more, then you can have a three-dimensionally solidified material that it is solid, but it contains a lot of liquid inside. And after the drying, and this drying process, people often use the supercritical drying using supercritical fluid at high pressure to avoid the shrinkage and cracking. So then you can have the aerogel, okay? But as I said, the silica aerogels are mechanically very weak. So this is a picture before silica aerogel is compressed. And during the compression, like the breaking typically starts like 10% compression or 10 to 15% of compression. So this is easily breakable material. So this is partly because the colloidal network structure consists of like this, the weak linkage of the small spherical silica colloids. So the linkage between the colloids are not very strong. So the overall silica aerogel doesn't have a good mechanical property or strength. Okay, so I can say the silica aerogels are mechanically friable. Friable means the material breaks with very small stress. It is like fragile, but it is, I have to say, it is friable due to the weakly connected colloids and high porosity. So as I said, people have to use high pressure supercritical drying to obtain aerogels. And also the handling and shaping of obtained aerogels are also difficult. So I believe these 2 points the biggest barrier for industrialization. And so we somehow want to add mechanical flexibility in the material. Before that, I will show up some about supercritical drying. Supercritical drying is a drying process using supercritical fluid. And as you know, over the critical point, higher pressure, higher temperature, there's a region of supercritical state. And at first, the liquid in the gel can go through the supercritical fluidic state, which doesn't have surface tension. Then you can avoid the shrinkage and cracking of the gel, okay? So after the supercritical state, you can you can decrease the pressure and temperature to make the fluid into gas. So this is a drying process. And we often use the carbon dioxide for the supercritical fluid because carbon dioxide has rather low critical temperature and pressure. But still the critical pressure is rather high, like over more than 7 megapascals, so more than 70 atmosphere. So I believe it should be avoided. So in the supercritical drying process, the drying goes like this. The first, the gel contains a liquid, then supercritical state, no shrinkage, no cracking, and after the drying, after decreasing the pressure, the gas in the pore, so the drying is finished. So as I said, this process should be avoided because you need a high pressure and a special apparatus for drying. But I also can say this is a very efficient process because the drying finishes like not like more than 10 hours, like a few hours. In a few hours, you can finish the drying. And this is a very time efficient process. So sometimes supercritical drying may be better than the ambient pressure drying, as I showed you later. Ambient pressure drying process takes a little bit much longer time. So what happens when gels are dried by evaporation rather than supercritical drying? You can see here, this is a common squid you haven't seen before. Have you eaten before? So by drying gels, you can see some shrinkage, even in the case of a squid. This is surume in Japanese. Have you tasted? Especially for non-Japanese. This is good with sake. Okay, but anyway, the gel undergoes shrinkage by the evaporation of the solvent. And this is the silica gel. Silica gel also causes shrinkage, but in this case, the gel is friable. So not only shrinkage, but also the breaking, cracking of the gel occurs. But yeah, so this is the schematic of the microstructure of the gel before drying. And during drying, there is shrinkage. And after drying, the whole things are collapsed. So you can't obtain aerogel normally in this process. So what we are trying is to make aerogels flexible, and make aerogels not from supercritical drying, but ambient pressure drying. So the difference is only one thing. The standard silica aerogel process, people use the tetra-functional alkoxysilane like TMOS or TEOS, but we use the tri-functional alkoxysilane with one methyl group. The methyl group doesn't react in the course of gelation and drying. So we can prepare lower cross-linking density flexible material with hydrophobic group from this precursor. And the chemical process of this precursor is a little bit complicated compared to that of silica aerogels. In the case of silica aerogels, it is easy to obtain the wet gel from this precursor by dissolving this precursor in methanol and the basic water. Then the reaction goes to form the gel, beautiful gel. It's very easy. Then you need to dry the gel by supercritical process. But in our process, this precursor doesn't form, this is the precursor forms the hydrophobic network in aqueous solution. So we have to prevent the phase separation in aqueous solution. So we use I don't go in detail, but we use the acid base two-step process to avoid, to promote the monolithic gelation. And also we use the surfactant to suppress the phase separation. But after forming the gel, we can obtain the aerogel by ambient pressure drying. So this photograph shows the flexibility of our, this is called PMSQ aerogel, based on the chemical composition of the gel, polymethylsilicone. A little bit difficult, but it is called, we can say PMSQ. So the PMSQ is flexible like this. This is 80% compression and then spring back to the original size without breaking, without any irreversible shrinkage. The network structure is like this. So the methyl groups can repel each other when compressed. So they show the spring back behavior. Okay. So this is actual drying process. I can say, I hope it works. No? Oh. It's very small. Can you see here? Let's start. Now the gel, the solvent evaporating started. So you can see the gel containing a hydrocarbon liquid shrinks slowly by the surface tension of the liquid. Now it's getting very small, like 70% shrinkage in volume. After when the pores are getting empty, then the gel size becomes larger again. You can see here. And now it's transparent, nice looking gel. So because of the compression flexibility, the gels can be dried by evaporation, even when the liquid surface tension of the liquid causes temporary shrinkage, they recover their size. Okay. This is because of the flexibility of our gel. So after drying, we compared the thermal conductivity of our aerogel, and I don't go in detail, but we found that the thermal conductivity is almost the same with the standard silica aerogels. They have low enough surface thermal conductivity. Okay. So, and now we can prepare like 30 centimeter square panel by the ambient pressure drying. So now you can see here in the Springer Handbook of Aerogels in the index, you can see this is now called Kanamori process. Like this. Please remember. So we are now updating the process of aerogel synthesis by using a different surfactant. In the previous process, I didn't say, but we used cationic surfactant to prevent phase separation. Then we got good aerogel showing flexibility against compression. So now we are using the polymeric surfactant. It is called poronic or poroxamer. Yeah, this is a process, about the same process by the acid-base two-step process in the presence of this surfactant. And the other point is to use the organic base, actually, but the whole process is quite similar. So with this surfactant, we can obtain bendable gels like this. This is the new aerogel, and because it has not spherical colloidal networks, but fiber networks like this. So mechanical flexibility is higher. So we can even prepare thin, like a wire of aerogel that can be knotted. So this is also a knot in a macro scale, okay? And you can see here that this is the 3-point bending test results. The previous PMSQ aerogel breaks in at the bending strain like 8 or 9%, but the new ones show a higher durability against bending. So it is like double durability. And one more thing we have to emphasize is the light transmittance also improved. So looking at the 3 materials here, this is a solid glass, this is borosilicate glass, and this is our aerogel. You can see the very good transparency. And you can confirm in the UV spectrum that our red curve aerogel shows the higher total light transmittance in all the visible light wavelength regions. Okay? So this really looks like a glass, not like aerogels. So in this new process, we also can prepare the aerogel by ambient pressure drying. Actually, this is rather difficult. There are some tricks, but it is now open in a paper, so you can refer to. And yeah, anyway, we can prepare the very good aerogel by ambient pressure drying, like in this case. So with this material, we are working on a startup company which locates in Kyoto and Tokyo. The name of the company is TM Factory, that we can prepare monoliths, granules, and blankets for different applications. Especially monoliths for window thermal insulation application is getting very, very important, like Professor Smalikov is already doing. So we can also prepare the monoliths for window applications. And TM Factory is also interested in the aerogels in design applications. So we are playing with unique looking aerogels for design materials. I like this, the lower left one. This is the aerogel granules in between the 2 glass plates, and the whole set of the glass plates and aerogel can rotate like this. Then the aerogel powders inside dances like a fluid, like a liquid. I like to see the movement of this one, because these are the particles are high porosity and hydrophobic, so they have very small interactions with each other, so they flow like liquid. And I also am working with artist. He's an artist and university professor, and he's making. He wants to create the sky with aerogel, because aerogel looks like a bluish solid because of the Rayleigh scattering. So I'm collaborating with him to give some advice for his artworks. Okay. So different one, PMSQ nanocellulose composite, like Professor Smarukov's. We have already also tried composite between PMSQ aerogel and cellulose nanofibers, and yeah, we got a bendable aerogel like this with a very good homogeneous porous structure, but it is not so transparent. So it is not very good for window applications. So yeah, just showing. Okay. And also collaborating with Dr. Tashiro in NIMS, we put the molecule that shows catalytic activity on the pore surface of our aerogel. And we found that this is the one. This is transparent, so we can do the reaction, photocatalytic reaction using the visible light. So the very good, we have very good catalytic activity, which is comparable with the homogeneous catalyst counterpart. So, okay. So this is also an extension to very soft, flexible material, not starting only from MTMS, but also we use here the difunctional alkoxysilane, which makes the network much more, how to say, softer. Then, but the network from these precursors are very hydrophobic, so it is difficult to suppress the phase separation completely. So the appearance of this gel is not transparent. This is white. So we named this gel like marshmallow gel. It is not eatable, but it looks like marshmallow. So we named it not marshmallow gel. And the pore structure is like this, micron size skeletons and pores. So it is easy to absorb liquid inside. And because of the rough surface and the low surface tension, low surface energy of the network, they show a very good hydrophobicity. And also they are flexible at very low temperature, like in the liquid nitrogen. They still maintain the flexibility, so we can put the marshmallow gel in the liquid nitrogen to soak up the liquid and then squeeze out in somewhere else, like this in this picture. So we showed that these materials can be used for oil-water separation because this aerogel, marshmallow gel, is completely hydrophobic. They don't absorb any water, so we can separate the oil, which is this one, red one, by simple soaking and squeezing out process by hand. We can separate the oil and water very easily. Then next, we tried to surface functionalization of this marshmallow gel because for fun, we wanted to make the surface of marshmallow gel oleophobic. So we prepared marshmallow gel from these vinyl functionalized precursors. Then after the preparation of the gel, we did surface modification with a perfluoroalkyl thiol by the use of thiol in reaction. Then we can add the oleophobic molecules on the pore surface. So we found that not only water, but also ethylene glycol, formamide, different organic liquids, even hexadecane, it has a very low surface tension. This material can repel all the liquid. Okay. So from the same vinyl functionalized precursor, but this is only from the trifunctional alkoxysilane. We can prepare also the transparent aerogel by the similar process. And after that, we show here you can see the network from this precursor. There are a lot of vinyl groups. So after the preparation, we can we can make the hydrocarbon chains by the radical reaction in a solution. So we can alter the mechanical property of this material. So this is the stress strain curves by uniaxial compression of the gels treated with different concentrations of AIBN, which is a radical initiator. So with the highest concentration of AIBN, the gel is like this, very stiff, like this, and shows spring back like this again. So but the pristine PVSQ, from the same precursor gel, they show rather weak, soft mechanical property and shows limited spring back behavior. After the treatment, it is very hard and perfect spring back because of the hydrocarbon chains. So in this process, we can prepare this is a pristine vinyl functionalized gel with the supercritical drying. Of course, you can prepare the aerogel, but ambient pressure drying, there's a lot of shrinkage. Most of the pores are collapsed. But after the treatment and ambient pressure drying, you can see here that you can prepare spring back behavior by spring back behavior, you can prepare a nice aerogels. So now we know that the hydrocarbon chains, not only siloxane networks, hydrocarbon chains also work for a better mechanical property. So we did an opposite way. First, we polymerized the vinyl groups to have the hydrocarbon chain, and then react hydrolysis and polycondensation for the process to form the polysiloxane network. Then the process is like this, polymerization and hydrolysis and polycondensation in a solvent. Then we can prepare the translucent aerogel like this. And we found that because this aerogel consists of hydrocarbon chains and both hydrocarbon chains and polysiloxane network. So this aerogel is very mechanically tough. So this is the compression and releasing behavior, not only one time, but also we can repeat this process like more than 100 times. It is very tough material because of the hydrocarbon chains. So, and when we prepare a thinner ones, like 1 millimeter thickness, it is like bendable like this. And also very tough, so we can put the once dried gel into a liquid again, and then dry it again. This is also possible now. And actually, aerogels are so friable, so it is very difficult to cut into shape with a nice technique. But with this tough material, you can see that we can cut the sheet of aerogel with a very ordinary knife into a very complex shape. Okay. We have many others, so I can't tell all the things. I'm sorry about this, but yeah, with the improvement and development of chemical processes, we can prepare now we can prepare aerogels from different precursors, like ethyl vinyl ones. This is from the unique precursor having organic bridges. Chloromethyl one, this part has reactivity, so we can use as a kind of surface functionalization. And this is what I said before already. Okay. So now, how long time I have? Until
10 more minutes or so, but because we need to leave a little bit of time for
Okay.
questions.
Okay. Okay. Thank you.
10, 15 minutes.
Okay. So you may know gels can be divided into two categories. One is the colloidal gel, like aerogels, like in this picture. They have a colloidal network inside, and they can be porous. And the other is the polymeric gel, like a swollen polymeric network. They can accommodate a lot of liquid inside. And the typical ones are for colloidal gels, like aerogel, and you can see here, this is a silica gel desiccant. You can find them in snacks and other foods to remove the moisture. And the other one is like this. You can find in your life, maybe in a restroom, the deodorant gel. You have seen before maybe. So we have played with the colloidal gel like this to because we are interested in the porous structure and mechanical properties in application of porous materials. But now I have in my mind, why don't we try to prepare hydrogels with unique flexible silicone materials? Because the hydrogels can accommodate liquid and also maybe functional molecules inside to show different functionalities, different from porous materials. So now we are trying to prepare hydrogels by using our technique to prepare the silicone network from alkoxysilanes. So this is one example. We now are preparing a gel from vinyltrimethoxysilane, and this is the co-network of methacrylate precursor. So these two precursors forms a double network, and we can prepare a nice gel. And also, we can put metal species. In this case, you can see here platinum. Platinum can coordinate to the vinyl group here. Oh, so low here. And also, if you have diphenylphosphine groups or pyridyl groups, you can accommodate palladium metal to the coordination sites. So in this way, now we can prepare hydrogels containing catalytically active complexes in the network. Okay. So now, yeah, we are trying to use the materials as a solid catalyst in organic synthesis, like hydroxylation reactions and also carbon-carbon coupling reactions like Heck reaction. Very good. Now we found this can be a very good catalyst because the network has flexible nature, so it is quite dynamic. Then they show a good reactivity against the substrates. Also, we are trying to prepare a very flexible hydrogels, like stretchable and compressible hydrogels. Like in this picture here, you can see the hydrogel before stretching, and after stretching. No, it's difficult to see this here. Okay, like more than 1,000% stretching strains. And also this is compressible, so very flexible. And now we are thinking of applications to biomedical purposes. And we are still now trying to improve the bioactivity improve the mechanical properties by designing the cross-linking structure in the network. And also, we have to put some bioactive species in the gel we are trying now. So this is the conclusions for my talk today. Thank you for listening. And I hope I could show you in our process, we can prepare glass-like, transparent, silicone type PMSQ. Aerogels can be prepared. And also we can see the macroscopic mechanical flexibility against compression and bending in the case of aerogels. And this mechanical flexibility allows ambient pressure drying to produce aerogels. Okay. Also, we are now trying to extend our research on aerogels to different type of hydrogels. And yeah, this is the whole research is for making functional materials and better mechanical properties by designing the molecular scale networks, also mesoscale networks. Everything can be done in our chemical process. Okay. Okay, so lastly, I have to thank all the co-workers up to now, especially I was a student under the guidance of Professor Kazuki Nakanishi, who is now a professor, the last year of the professor in Nagoya University. He's 65, so the last year. And I also got many funds for research. Thank you so much. So, and thank you for your attention.